Hello. So as I said at the end of the last video, there are a lot of possible estimators for any estimation problem. And then how can we tell what is a good estimator? The basic idea is from the randomness of an estimator. So think about this. An estimator is calculated from a sample, like sample average. You should be able to calculate the estimator. And if you repeat the random sampling, each time you are going to get a different value of the estimator, right? So sample average can be different when you have a different set of observations. So it's random. Therefore, it's random, and then it will have a sampling distribution. So it is random and it follows a sampling distribution. So we are going to evaluate an estimator using its sampling distribution. For example, the perfect estimator will satisfy this condition: probability that your estimator equals to the true parameter. This is the probability that your estimator is correct. If this probability is 1, that means your estimator is always correct. And that means you know the answer. So such an estimator does not exist. If it exists, then it's too trivial. So it's not a statistical question at all. So anyhow, the idea is an estimator has a sampling distribution, and we are interested in how the sampling distribution looks like relative to the true parameter. So of course, the better the distribution is closer to the true parameter. For example, so think about this. The sampling distribution of an estimator relative to the true parameter looks like this. So say true parameter is the red, and when you repeat estimation, say, so true parameter, this is the percentage of voters supporting a certain candidate, and so the answer is here. And then to estimate this parameter, you survey 1,000 people. And from the first survey, for example, you get a point here, which is smaller than the true percentage. But if you repeat the survey again, another 1,000 people, then you may get somewhere here. Now it is greater than the true parameter. And so like that, as you repeat the random sampling or the survey, and then you are going to get different values. And when you repeat that infinite number of times, you will see this distribution. So when you do the estimation once, you are most likely to get somewhere here. The probability around here is the highest probability here, but the probability of this much wrong outcome, wrong estimator, is very unlikely. Also, this much wrong estimator is also very unlikely. So your estimator will be around here with following this property, following this probability density. And now think about this. Suppose that your estimator happens to be here. When you survey 1,000 people, your estimator happens to be here. Then it is this much different from the true parameter. So we say the difference is the estimation error. So when you calculate the parameter from one sample, then there is one estimation error. If you are lucky, super lucky, estimation error will be 0, but that's very small probability, and especially if the sampling distribution is continuous, then the probability that the estimation error equals to 0 is 0. Probability of 1 point is 0. So So you cannot imagine your estimator exactly hits this point. So that is unlikely. But still what you can say here is your estimator does not deviate that much, like unlikely here and unlikely here. Or you may analyze, you may read the sampling distribution this way. The area on the right side of the true parameter is the probability that your estimator lies on the right side of the true parameter, which means your estimator is greater than the true parameter. So this area is the overestimation probability, right? So you may calculate overestimation probability in this way, or similarly, you may calculate the underestimation probability. So underestimation probability is this area. Like this, you may calculate any area you want if you had the sampling distribution. So the sampling distribution tells you the probability of your error. How small, how big, how likely is your error. So that's how we are going to evaluate and compare estimators. And let's think about this. So now we are comparing two estimators. Suppose that there is a blue estimator or blue estimation method and orange estimation method. These two different estimation methods. For example, you may think blue is sample mean and orange is something else like sample median or sample mean after taking out the minimum, for example. And their sampling distribution will be different. And in this case, when you compare these two, blue estimator is correctly centered at the true parameter. It's centered at the true parameter, so even if it may be wrong, but on average, you can expect it is around the true parameter. But the orange estimation method, is centered around here, centered at here, which means on average, the orange estimation overestimates. It's larger, so the overestimation probability is larger, and the center is larger. So you can say that orange estimator tends to overestimate the parameter. So in that sense, orange estimator is worse than the blue estimator in this dimension. Or you may compare these two. For example, the blue and the green are both centered at the true parameter, which is good. So both are correctly centered, but their problem is the spread, the dispersion. So green has larger variance, which means, so when you use the blue estimator, the probability outside this much area is very small. So probability smaller than this point is very small for the blue estimator. However, the green estimator still has some probability on this area, which means the green estimator is likely to be more wrong, or higher probability of being more wrong. And same thing can be said here. So the green estimator has thicker tails, so larger errors happen more frequently in the green method. So the green method tends to have larger estimation errors than the blue estimator. So these are two dimensions we may compare. We can compare two estimators. So to summarize, typically there are two commonly used criteria. Theoretically, there are more theories about how to evaluate estimators, but I'm going to introduce two criteria. One is whether the sampling distribution is correctly centered. So the mean of the sampling, the estimator, so mean of the sampling distribution equals the true parameter. Like this, like the blue one. Blue one satisfies that criterion, but the orange does not. Orange is overestimating. And the second criteria is about the variance. So the variance of the estimator calculated from the sampling distribution should be small. The smaller the better. So again, in this graph, the blue estimator has smaller variance, so it's less likely to deviate much. It's more compact, which is good, which is a desirable property as an estimator. The problem here is, so when I explain this, it sounds too easy and obvious, but it's actually not that easy because think about it. We are just imagining, we imagine the sampling distribution is observed, and we imagine the true parameter is here. But actually, the true parameter is unknown. When you estimate something, you are estimating because the true parameter is unknown. So you cannot fix where is the true parameter, right? And also, the estimation cannot be repeated. Theoretically, hypothetically, you can resample, reimagine sampling, random sampling again and again, but in practice, that's not possible. So what you have is just one observation from this distribution. You cannot make any distribution from repetitions. So this graph is purely theoretical. What I explained is purely theoretical, and they cannot be deducted from the. They cannot be deduced from the sample. So that's where many students are confused. Remember so these sampling distribution and the location of true parameter is never observed. They are never observed like a data set or like throwing a dice. So we have to proceed our argument purely theoretically. And it's not that difficult because we already learned the central limit theorem. We know the answer. Everything is normal. So it's not that difficult. Okay, I'm going to continue the details in the next video, and I hope you find it enjoyable. Thank you.